Hi, this is an overview of UCI. I'm recording it primarily for myself because I know that I'll forget the details later on, and then I can fall back on this video. But also for if anyone else wants to get an overview of the UCI spec, they can go through this video. So I'll time tag different sections in a file in the same folder where I put this video and also the slides. So basically I've arranged it this way. So this is derived from kind of the table of contents. Let me see. Here is the table of contents of the UCI spec. So it starts with the intro and overall UCI components, and we have three layers, and we have section 2, 3, and 4 for 4 and 5 for third layer, and then we have sideband and configurations and interface definitions. Compliance is just a one pager, so and I haven't gone through the appendices. So this is the same thing. This is the outline of overall presentation with this kind of same content, except that at start we have a PCI and CXL overview because UCI is built on top of that. So we need to have some basic understanding of that. So I'm not an expert on any of those, but I went through some of online resources and collected them in this presentation to give a quick and dirty overview at the start. So we'll first start with PCI, the oldest of the standards here. So PCI is a hierarchical system, which means that there's a single source. In most of the cases, that's CPU connected to a bunch of devices using root complex, and the end components are generally called endpoints. A root complex is the system that connects CPU with the rest of the memory and peripherals. There are other components like repeater, which is used to improve the signal quality, and there are basically two categories of that: retimers and redrivers. Redrivers basically are kind of amplifiers, and retimers are more complex than redrivers. They resample and kind of replay the signal. An endpoint is a general term for PCI end component. Switches can be used to expand the PCI, and this can be done by having more lanes, for example. There are two kinds of switches: fan-out switches, which are a bit simpler, and fabric switches, which are a bit more complex. We often use PCI devices in a slot and in our PCs or servers, and the basic unit, basic way to transfer data is using two differential signal pairs for TX and RX, and one set of this TX and RX pairs is called a lane. So there can the by 1, by 4, by 8, or by 16, or by 2 are different kinds of lanes that if we increase the lanes to 4, 8, or 16, then we denote it by in this way. So that also represent so the slot size increases accordingly. The PCI protocol has three layers: physical layer, data link layer, and transaction layers. So there are following types of transactions. Memory transactions are transactions to memory map locations. Then we have IO transactions, which are transfers to IO map locations. In addition to that, we have transfers to configuration space, basically to configure or set up devices. And PCI also adds different messages between PCI devices, and such kind of transactions are called message transactions. Uh, so let's quickly go through the layers one by one. The bottom layer is file layer, and file layer is further subdivided into electrical block and logical block. So logical block is more like bit manipulations, and electrical block actually then converts it to the physical signal. So the logical subblock basically does data scrambling, and it also does 8-bit 10-bit encoding. So basically, scrambling and encoding combined ensures that even if we don't want to transmit, we are not transmitting. Even even if we are transmitting zeros, there are still enough transitions in the signal so that on the receiver side, a clock can be extracted based on that signal. So that's one use of encoding. And after in 8-bit 10-bit encoding, we actually convert 8 bits into 10 bits, and 2 extra bits are added, and that encoding makes sure that we have enough transitions. In the later variants, it was changed. I don't remember exact numbers, but I think we had 2 or 4 bits in 128 bits, or something like that. So after that, we frame the packet. We add start of frame and end of frame symbols. So that after framing, that data is given to the electrical subblock. Electrical subblock converts the parallel data into serial data, and transmits it over the channel. On the RX side, RX receives serial data, and it converts it into parallel data and gives it back to the logical subblock, where again we do the reverse process. We find the framing symbols, and we remove them. Then we do 8-bit 10-bit decoding and descramble it, and we get the packets back. So on the receive side, we also do the clock recovery, and in addition to that, if there are multiple lanes, then there is skew between that, because PCI was initially meant to be standard for peripherals. So on the PCBs, we allow 20 nanosecond lane to lane deskew. So so, so that is compensated, and basically electrical layer does the differential signaling. Differential signaling means that if we want to transmit one, we send one on the P side and -1 on the negative side, and vice versa for transmitting 0. uh, there is a PLL which takes 100 megahertz clock input, and then it multiplies it to generate 2.5 gigahertz clock. It uses AC coupling, and there are also some other details about de-emphasis to reduce intersymbol interference. Okay, so the layer above physical layer is data link layer. Data link layer basically adds a sequence number, a 12-bit sequence number, plus 4-bit reserved to the TLP that it receives from the transaction layer. So if these brackets show the transaction layer packet, and we add the sequence number, and also add the CRC protection. In addition to that, data link layer supports retries. So if the data is received correctly on the other side, that is, there is no CRC error, we'll get a ACK from receiver. But if there is a NAC instead, So that means that we have to retransmit the TLP. That also means that we have to store data till we get a NAC. So we have to have a retry buffer in the data link layer. So data link layer are strictly associated with that given link. So if so the transaction layer, for example, can have multiple targets or to which it can send data, but the data link layer is strictly connected to the other side of data link layer, its link partner. So the packets that TLP data link layer also has some data link layer packets called DLLPs. So for example, ACK, NAC, and flow control packets plus power management packets. So so data link layer also tracks the state of the links and communicates that status with the both the transaction and file layer. So states like whether the data link is active or an init or inactive. So it has status outputs DL up or DL down. Transaction layer basically, in general, in any protocol, basically transaction layer adds a header that contains the identification information for the payload, and it also adds digest or at the end, which may be CRC in this case, and this is optional. So I'm not covering the individual bits of the header in this case. Uh, so while handling, if there we get a if a TLP is not supported, it generates a non-fatal error. Similarly, if we get a completion of a type that was not supported, then it also results in a non-fatal error. So, in summary, if a payload comes, we add header and digest, and then it becomes a TLP packet. Then on the TLP, the data link layer will add a sequence number and CRC, and it will be given to electrical layer, which will scramble these packets and do the 8-bit 10-bit encoding, frame the packets and serialize it, give it to the channel, and then it will be received on the RX, framing will be removed, and 8-bit 10-bit decoding, packet descrambling, and then that parallel data is given to the data link layer. If it is received correctly, there are no CRC errors, then we send an ACK and give the data to the transaction layer, which extracts the headers and give the payload back to the receiver. So this is the overview of PCI protocol. Kind of. So PCI 6 is the latest variant, and it has done some fundamental changes. First of all, the signaling is PAM4. So that means we double the data rate, but at the trade-off of higher bit error rate. To counter for that error rate, a lightweight FEC and retry is added to the to PCI 6. The main aim was to have the lowest latency possible, and that's for the newer use cases of accelerators over the PCI. PCI 6 is flat based, and each flat is 256 bytes. The division is given here. It's backward compatible. Previous ones were not flat based. So once it gets into flat mode, it remains in flat mode. Replay is supported. So since if there are errors, we can replay a specific flat or replay from a flat onwards. So so there are two options: replay from flat n or replay only flat n. So it's byte by byte interleaved in three levels. I'll show a diagram about that. This diagram shows that if we get a NAC and we want to replay flat number 13, so that will be sent, this blue one. Or we can also have a NAC with replay from flat number 19. It will replay the flits from flit number 19 onwards. If the no flits can be are not required to be replayed. This is the diagram that I was referring. Different colors are referring to the interleaved bytes. So these blue kind of bytes are result in one FEC and ECC 0 here, and then this orange are getting into ECC1, and these blues are getting into ECC2. Okay, so there is a new low power mode LP0 in PCI 6 which maintains at least one active lane to carry on traffic and lets rest of the lanes are in power saving mode, and that can be negotiated. For example, this diagram shows that if we enable L0 mode, then we have only one lane enabled, then we request 8 lanes, and if we get the ACK for that, then 8 lane 8 to 15 will go electrically idle and will get transmission on lane 0 to 7, and later on if we request 16 lanes, then rest of the lanes will go through retrain while we receive the traffic on 0 to 7. Okay, so now let's cover CXL quickly. So basically CXL adds cache and memory semantics over the PCI file layer. The main use cases for accelerators. And this is done by multiplexing between three kinds of protocols: CXL IO, which refers to the traditional PCI devices, and CSL cache and CSL mem. CXL cache basically, if we want, if accelerator wants to cache the memory of the host, and CXL mem is used for the other way around, if the if the host wants to cache the memory of the accelerator. So these are kind of three cases. So this diagram tries to explain it. On the right side, we have the host processor, which already has coherency mechanism for probably its multiple cores. So it is connected to the CXL device, and CXL has the same PCI PHY, but on top of that, there is a CXL logical file layer, which multiplexes between these three protocols that we just talked about: IO, cache, and memory protocols. So the cache protocol is kind of similar to the messy protocol, where to ensure that the cache coherence between CPU and the accelerator. So the main thing is that it's asymmetric. So the functionality of the host agent that is doing the cache coherence is not required at the accelerator. So accelerator is kind of another core that is trying to access the host memory. Um, Similarly, if the CPU wants to access the host access the device memory, it will use CXL mem transactions. There are three kind of devices based on that. So first is the devices which have only CXL IO and cache. So these are typical smart NICs or simple accelerators where we have an accelerator implemented as a NIC, and then the processor, the accelerator wants to cache the memory of the processor, so it can use CXL.cache semantics there. For dense computation cases where the accelerator wants to cache the memory, but processor also wants to use the high bandwidth memory that is available on the accelerator, then we need CXL mem semantics as well to for the other way around. And type 3 devices are the devices that are called memory buffers, and here it's not an accelerator but basically expanding the memory of the processor, and processor can access the CXL device memory using CXL mem protocol. The CXL IO is required in all cases, so it's the cache and mem that we can choose. So CXL 2 has the main aim to expand it from single host to connection between multiple hosts. So the main idea is to expand it to the data centers where basically for the top of the rack switches that support for those. So main thing that it supports in 2.0 is switching, pooling, and disaggregation, hot plug support, and support for persistent memory and security. So, so this diagram shows how it's shows the main idea. So in a one CXL one case, we only had simply one processor and one accelerator use case. So in 2.0, we have on the right, we have this switch which can using which we can assign different resources. For example, the bottom row can be thought of as multiple resources like memory, and different CPUs can have access to different memory resources using the CXL switch, which is basically the top of the rack switch connecting uh, uh, different drawers to of CPU to maybe drawers of memory. So it also the color coding here shows that let's say processor 1 is using these two memories and processor 4 is using this memory. And we can also have a vertical split that instead of having one physical device memory, we can divide it into multiple logical memories and have a better granularity in assigning resources to the course. There is a thing called Fabric Manager that I haven't studied, but it's also standardized in CXL 2.0. This is the list of list of the features added in CXL 2.0. CXL 3.0 basically further enhances it by enabling peer-to-peer memory sharing in a coherent way, and support for all kind of devices under a switch, support for multiple hosts, which is increased from 16 to 496, doubles the data rate because it's PCI 6 based, so it has better data rate. So the peer-to-peer sharing is enabled using a back invalidate signal to the host. So in the common cases, we'll get the data from the other peer instantly if there is if the data is not shared by the host, but if it is, then the backend validate will tell us about it, and we'll have to wait for to get the right to get the non-dirty copy. So it's based on PCI flat format. So there are two kinds of flat formats in PCI. One is called standard flat format, the top two bars. Here we have a single FEC for the complete 256 bytes. In latency optimized flat layout, we have CRC for 128 bits. So that means that the data can be consumed even when we get the 128 bits instead of waiting for the complete 256 bits. So that improves the latency. Sorry, I was using the term bits. It was actually bytes. So 128 bytes and 256 bytes. Sorry for that. Okay, now having idea about these PCI and CXL, we can now jump into UCI. So UCI is basically used to connect chiplets on on the same package, as well as chiplets on another package using retimers. So this is a typical chiplet where we have multiple CPUs connected using UCI and also connected to IO tile using UCI link, and CPUs connected to the accelerator using UCI link. So these are all chiplets connected on a package. So the main idea is to use PCI or CXL semantics on the upper layer, but change the file layer and have a UCI file layer instead. So, so that's the main idea. So that I've already told IOTile can also provide external CXL pins to the DDR or other devices. Similarly, accelerator can also be connected to CPU using PCI transactions running on the UCI. So, so UCI supports PCI, CXL, or any custom protocol. So this diagram explains it a little bit in more detail. So on the left side we have this rack with a top of rack switch and different drawers of compute, and these are connected to the switch on the top, which connects those processors to the pooled memory drawer. So basically, this is the figure that we already have seen in the CXL review kind of short video. So, so this is basically the same thing. This top of rack block, that this switch connects these host lines are coming from the compute, and we are connecting it using CPU CXL switch to the memory drawer. So so basically the here the top right one is the compute drawers, and bottom ones are this switch, and you can see that to go off package, these green lines are going off package to another package. So these are connected using retimers to the off package to the other package. So this package is connected to this package using these connections, that long reach media connections, and such connections are supported using CXL retimers. So so these hosts are this way connected to the to the devices. So the switch on one side is connected using retimers to the cores, and the other on the other side it is connected to the memory devices. There are two kinds of packages supported in UCI. One is called standard package. It has kind of bigger bump pitch, and also but less number of pins. The advanced package has higher bandwidth, low latency, but and a small bump pitch, but also has shorter reach. So these are different packaging technologies that can be used to connect the advanced packages. So in these tables we can see that the bump pitch is 100 micrometer for standard, but 25 micrometer to 55 micrometer for advanced package. Its reach is 2 millimeter as compared to the reach of 10 millimeter or 25 millimeter in case of a standard package. So this is the overview of the layers of UCI Express. So at the top we have protocol layer. It supports PCI and CXL and streaming protocols. Then we have die-to-die adapter layer, and then we have physical layer. So these are the protocols supported. For die-to-die adapter layer, we have arbitration and muxing, because in CXL we have CXL IO or CXL mem or CXL cache, so we have to mux between them. So that muxing is part of die-to-die adapter layer. Also CRC and retry mechanism is also in this layer, and link state management and parameter negotiation. If the bit error rate is less than 10 to the power minus 27, then we need a retry scheme. And then in the PHY we have link training, repair, reversal, scrambling, rescrambling. We will go into these details when we come to the PHY layer details. In the PHY layer, basically it's further divided into PHY logic and electrical layer, basically the front end. So it consists of of modules. Each module is kind of a single slice with k lines connected to the other side. We have a data interface shown in dark blue here, and we also have sideband interface, which has clock and data in both directions, to have sideband messaging, which is used for many things that we'll discuss later. So, so that many things are basically parameter exchanges and register access and coordination with the remote partner, link management and training. It has a forwarded clock pin for of 800 megahertz and a data pin in each direction, and it's always on. Each module, so there can be multiple such modules, so each module has its own set of sideband pins. For advanced package, we have redundant pair of clocks and data pins in each direction for repair. And the main band has a forwarded clock, a data pin, and n lanes per module. For advanced, it's n is equal to 64, and we have 4 extra pins for lane repair. For standard package, we have 16 such pins. The Interface between protocol and die-to-die adapter layer is called flit-aware die-to-die interface, or FDI. And the protocol between the interface between die-to-die adapter and PHY is called raw die-to-die interface, or RDI. The purpose of highlighting it here is because RDI and FDI will be used quite a lot throughout the presentation, so we should always know that the top one is FDI and the bottom one is RDI. So these interfaces are defined to reduce the basically development and testing costs, so that we have standard IPs available by different vendors that can be used to test things. So in single module configuration, for example, an advanced package will have 64 such lines, and for standard package will have 16 lines. In multi-module configuration, we will have a multi-module PHY logic on top of PHY. So there will be a single die-to-die adapter layer. So PHY will be handling the multiple PHYs, and in this case. Similarly, we can have four module configuration as well. So this is one thing. Uh, if we go beyond package, then we need to use retimers. So in retimers, so on the left we have one package, on the right we have another one, and this die is talking to this retimer, and retimer is going off package and talking to the other retimer. So each retimer has a receiver buffer associated with it. The main responsibilities are reliable fit transfer across the off-package interconnect. We can have native protocols, FEC and CRC. For example, we'll see in a little bit later that in raw mode we do that. And timer also provides FEC, CRC. Can also provide SON, FEC, CRC, and retry. Um, so DAX and DAX on the local side and remote are independent of each other. Or a retimer can replace PCI and CXL FSC, or use its FSC, use its own FSC, but use the underlying CRC and replay mechanism. In addition to reliable transfer using the FSC and CRC, retimer also is used for resolution of protocol parameters, and its implementation define both sides negotiate at start, and there is a stall signal that can be a stall response that can be used to avoid timeouts. So during negotiation, so a timeout is 8 millisecond, and after 4 millisecond we send a stall response if we don't want time. In addition to that, the timer also resolves linked states. The so the PHY states are called RDI states, and the die-to-die adapter states are called LSM states. Additionally, it also has flow control, which is credit based, where each credit represents 256 byte of data in the receive buffer. So in the initial parameters exchange, we advertise the credits, and credits returns are then managed using valid framing that we'll discuss later. No credits between the timer and the die at the die-to-die adapter. So basically, so on the remote side we have credits, but on the local side we don't have credits. Some of the performance targets and interoperability details in chapter 1 are skipped in this slide. Now let's cover the chapter regarding protocol layer, which is the top layer. So basically, as mentioned earlier, UCIe supports PCIe and CXL protocols. So I'll be skipping some of the slides, and some of the details are not fully clear to me as well, but I'll try to give whatever I can explain here. So assuming, so these in this chapter, basically the assumption was to that 64 byte, we have a 64 byte protocol layer data path and 64 lane advanced packet module. So we can we're transmitting 64 bytes at a time. So for PCI 6, we can have two modes, raw mode and standard 256 byte flat. So in raw mode, basically, if assuming the 64 byte protocol layer data path, we just forward use all of those as data. So in the 256 byte flat mode, we convert it into 256 byte flats. So the gray fields here are to be filled by the adapter, and from the protocol layer that will be driven as zeros, that will be overridden by the adapter. For CXL3, 256 byte flat mode or CXL 256 byte flat mode, we have three kind of formats. One is raw mode, which is similar to the one we already discussed, and for latency optimized mode, we have again two formats. One is for CXL IO and one is for CXL cache or mem. So as we discussed in the CXL video, that in the latency optimized mode we have CRC at 128 byte boundaries. So that's why we have CRC here and CRC here, and similarly CRC here and CRC here. So there are some differences between IO and cache mem that I don't fully understand. So we have header here and these CRC bytes here, but rest of the bits are a bit different. For standard mode, we don't have CRC at 128 byte boundary, and we have header at first 2 bytes and 14 bytes to be filled by adapter. So ACNAC, power management and link management DLLPs are not used over CXI for CXL IO for any 256 byte flat modes. I don't know the reason why, but that's from the document. Also, I don't know the term viral containment and how it is used, but from my understanding, if we don't want to send data onward, we can corrupt the CRC bits. Okay. So the third option is CXL 2.0 or CXL 68 byte enhanced flat mode. So since it's a 68 byte mode and we are transmitting over 64 bytes, so it won't be aligned every time. So we have 2 byte header and 2 byte CRC and 64 bytes of data. So this data ends here and we get consecutive packets. So in the next header is here and then CRC here and so on. Again, PM power management, ACK, NAC, DLPs are not supported for CXL. So for CXL IO transmitter must not implement retry in protocol because retry is handled in the adapter. So it must still drive LCRC bytes to 0. For streaming protocol is basically raw mode in which we can have any custom protocol that can transmit data in the so the format is similar to the raw mode that we initially saw. This kind of format is used for streaming mode. Okay, so the next So this table just basically shows that for PCI 6.0, raw mode is optional, but this mode is mandatory. For 2.0, raw mode is optional, but 68-byte flip mode is mandatory. And similarly for 256-byte mode, standard flit is optional, but strongly recommended to have latency optimized mode as well. For streaming protocol, we just need the ROM. Okay, so now let's cover the die-to-die adapter chapter of the spec. So basically, die-to-die adapter layer is responsible for reliable data transfer. So that means that CRC, retry, and parity bits are handled here. We have arbitration and muxing if we have multiple protocol layers, link state management, and protocol and parameter negotiation with the remote link partner. So why is arbitration and muxing required? If it's a single protocol, then we don't need anything. If PCI or streaming protocol, but if we have CXL, then we have to multiplex between CXL IO or CXL cache mem. And similarly, if we have multiple protocols on top, we can have multiplexing between them as well. But those both the protocols need to be the same if we want to do that. So they have to be rate matched, and they'll be running at half rate. So, no offlets are added if there is if one of them doesn't want to transfer anything, then we insert no offlets. And but no offlet can actually bypass retry buffer. So both protocols, if we are muxing to, should have same protocol and same formats. Okay, so this diagram shows the link initialization stages. So first of all, stage 0 is that die specific, any reset flow in the die specific things, and it can happen independently. So that's why we have different lengths shown here. So this die took a little bit more time to come out of reset. Once the board die is come out of reset, we first of all we do sideband detection and training. So there's a separate chapter on sideband, so that will be covered then. And after that we have main band training and repair, and sideband training parameters exchange. So so that will also be covered later. And stage 3 is basically parameter exchange between adapters to negotiate the protocol and platform. So these two will be done later, but the protocol exchange thing, parameter exchange is discussed here. So, so basically, first of all, the die-to-die adapter layer determines its own capabilities, whether retry is supported, and how many credits to advertise. And then we exchange those parameters with the remote link partner. Basically, in the curly brackets, we normally show sideband messages. So this is a specific sideband message that is the capabilities of adapter that the downstream port sends advertising its capabilities. The upstream port sends its capabilities in response, and then downstream port sends another message, final capabilities, to have the common subset that can work. After that, after these three messages, sideband messages exchanges, FDI bring up happens, that will cover later. So this is the visual representation of the same thing, that we have a from downstream port we have a capabilities message sent to the upstream port, and upstream port also sends its message, and we have then final capabilities message. So, so how do we advertise these capabilities? So this is basically inside the message we have a bit vector representing different things. So for example, whether it's a raw mode or not, whether it's a 68 byte flit mode, whether it's 256 byte flit mode, PCI flit mode, whether it's streaming, is retry supported, multiple protocols are enabled or not. If they are enabled, then stack 0 and 1 both should be enabled. Then we have two different formats for latency optimized packets, and whether the device is retimer. If yes, then retimer how many credits. So it's a whether it's a downstream port or upstream port. So all these corresponding bit is set if it's true. So if it's 68 byte flit mode or 256 byte flit mode of CXL, then extra handshake is required as well. So here we had the regular handshake with advertised capabilities of adapter and advertised capabilities from the upstream port and final capabilities. After that, we have another handshake, and this time it's advertised capabilities of CXL and advertised capabilities of CXL from the upstream port and final capabilities of CXL. So for parameter exchange, timeout is of 8 millisecond. If we get a stall message, then timer resets. So if we need more time, we can send stall messages. Retimers must resolve capabilities from remote side before responding to parameter exchange with its own die. Uh, okay. So here we see a comparison between the different protocols that we discuss in the protocol chapter and the modes of preparation in this kind of chapter. So raw mode is for all kind of protocols. So it's optional for everyone except the streaming protocol. So in raw mode, we just use all the bandwidth available to send whatever we want to send. The CXL 2.0 or 68 byte flit mode is basically referring to this thing, this 68 byte flit mode. The format we already discussed in the protocols or a little bit earlier. We have this header and then we have CRC. So here we have the detailed format of the header. There are two kinds of format. One is if retry is supported, and one is if retry is not supported. So if retry is not supported, then we have protocol identifier, which protocol it is. So here we have different options, whether it's IO or cache or ARM split, identification of stacks, whether it's regular flat header or pause of data stream flat header. If we don't want to transmit something, we use pause of data stream. Okay. And if retry is supported, then we have this ACK and NACK kind of resources. Sorry, ACK and NACK bits. And also some sequence number bits. So, so pause of data stream is used when we have nothing to send, and here is the bits that we use. That we some of the bits will be set, and sequence number will be flipped while sending pause of data stream. Okay. For PCI 6 or CXL standard 256 byte, we have 2 byte header and 14 bytes are reserved for adapter. And this refers to the standard 256 byte mode. For PCI or CXL. So um, so as discussed earlier, that there are some bits here as well that I'm not fully sure of what they're. It requires a bit of understanding of CXL protocol and PCI, which are lengthy documents on their own, so which I didn't see. So, but here's the header format for it. Uh, so there are multiple formats supported. One is kind of sorry. So these are the format 3 or format 4 without retry, and then we have format 3 and format 4 with retry, and so for PXL and CXL IO protocols, the LLPs basically bypass TX retry buffer, so they are partially filled by protocol layer and partially by the adapter layer, and these kind of gray shade things are that are filled by partially filled by protocol and partially filled by adapter. But I don't know the exact meanings of these bits. For 256 byte flat mode and latency with latency optimized flat, we have these kind of CRC at 128 byte, and we have already seen this, but now we can see the details of headers. These are the tables that are kind of pretty straightforward, but they're telling us that which bits correspond to how to identify which protocol it is based on different bits in the final capabilities in CXL or adapter message bits. So you can go through that yourself. So basically, these are the different formats that are supported. So then we had this kind of state machine hierarchy. Uh, for PCI or streaming case, we have adapter LSMs in the die-to-die adapter layer, and in the physical layer, we have our RDI state machine. For CXL, we also have state machines for the different CXL IO and CXL MEM kind of protocols, and these are called VLSMs. So, but the adapter has its own LSM, and above that we have these muxed VLSMs. So adapter link state machine basically coordinates link states with the remote partner, and each protocol stack has its own adapter LSM. The FDI interface has PL state status bits that these states are exposed there. As I already told, for CXL we have R, MUX, VLSMs, while in PCI we only have LSMs. Uh, uh, so if we have multiple modules, still we have a single RDI state machine. So that detail is abstracted out in the file here. So multi-module PHY basically creates that abstraction. So the adapter LSMs and the RDI LSMs are coordinated using sideband messages. So we'll cover some of those later, but these curly brackets shows that these are sideband messages. But the VLSMs are controlled by main band messages. So these ALMPs are ARMUX link management packets that are sent over main band. So so basically this first of all, the RDI state machines become active, and then adapter state machines, and then VLSMs. So this is kind of state diagram from a later chapter that we'll cover in a little bit more detail later. So so for power management, entry sequence protocol layer basically sends a PM entry request. So power management refers to entering a low power state or coming out of low power state. So here we are talking about entering into a low power state. There are two such states, L1 and L2. For CXL, if there is a protocol request, then we send RMUX link layer management packets to on the main band. For PCI, we decide based on idle time whether we want to go into power saving or not. So then die-to-die adapter link state machine enters into power management, and then PM entry on the RDI side, basically on the PHY side, and PHY then moves to a deeper PM state and takes necessary action for power management. For exit, we have the reverse action. We get an active request from protocol layer across the FDI and RDI interface to the local physical layer. The PHY then uses sideband to send wake up signal to the partner. So once RDI interface is active and is in active state on both sides, the adapter LSMs exit PM, and after that, protocol layer becomes active on the SDI, on the FDI. But for CXL, we have ALMP exchanges on the main band for each state machine to be on the active side. So the CRC computation in the is basically done using a linear feedback shift register, and its Verilog code is also given in the appendix, I guess. So that's basically a straightforward forward computation. So we can skip that probably. We can do runtime link testing using parity bits. So basically, we can detect the link health at the runtime, and that is done by periodically injecting parity bytes in the middle of data stream, if this mechanism is enabled. And receiver checks and logs those parity errors. Basically, adapter inserts 64 into n bytes every 256 into 256 into n bytes of data. N comes from a control register. If we want to do that, we just send a parity feature request sideband messages, and we get an ACK or an ACK. So this is kind of that thing that we send a request, we get an ACK, and then we start sending those bytes. If we get a nag, that means that feature is not supported. Okay, let's now move to the logical file layer. So basically, the file layer can be divided into two parts, the electrical layer and the logical layer. So first we'll cover the logical file layer. So main things that it does is link initialization, training, and power management, byte to lane mapping for data transmission, um, a redundancy remapping, sideband messages, scrambling, and training pattern generation, lane reversal, and with degradation. We'll cover these things in a moment. So first thing is byte to lane mapping. So this is how the bits are transmitted. So we have clock, valid, and data. So valid remains high for first half of the unit interval and remains low for the second half. We have double data rate transfer, so we transmit bit on rising and falling edges. So so there are a bunch of tables like this in this chapter, but I've skipped others. But this because they are similar, but for different interface widths. For example, here we have 64-bit interface. So byte 0 is mapped to lane number 0, and byte 1 is mapped to lane number 1, and so on up to byte number 64, 63, and 64 is again mapped to byte numbers lane number 0, and so on. So that means that on the lane number 0, that byte will be transmitted in the order shown here in 8 UIs. So there are similar figures for 32-bit interface, for 16-bit interface, and also for 8 lane interface. That's because in case of if there are errors on some lanes, then we can degrade the standard package to by 8 package as well instead of by 16. So but that's also done in a similar way than that mapping. So, but you can see the tables from the spec. Um, there is another thing that's valid framing. We discussed earlier that credit returns are done using valid framing. So what I understand from here is, but I'm not fully sure about this, that if we want to return credit, then instead of having valid 0 for this period, we can have it all ones here. So that will return one credit. So this table, that's my understanding of this table, but I had some doubts because in all the diagrams valid was high for half of the time and low for half of the time, but from the table it seems so that that's not the case. So for example, if we want to transmit data only, so no credit release, then this is the case shown in the diagram, that 4 ones and 4 zeros. But if we don't want to send data and we only want to send a credit, then valid will be 0 for the first 4 cycles and 1 for the next 4 transfers. And if we want to send data plus credit, then it will be all ones. So that's my understanding. Um, uh, after after providing data, if again after 16 UIs we have no other transfer, then we can gate the clocks. So that is this figure shows that after the transfer we have 16 UIs, and after that we just get the clock. So unless there is another mode, free running clock mode, if that is negotiated, then clock will keep talking. So sideband packets, I told earlier that we have basically main band and a sideband. So in sideband we only have a clock and a single bit of data in both directions. So so we transmit 64 bits of data, and then we have 32 unit intervals of no activity, and then again 64 bits of data, and so on. So basically our sideband packets have a 64-bit header and 32-bit or 64-bit data. 32-bit data is also sent using the 64-bit serial packet, but MSBs are padded with zeros. Devices also must support lane reversal within a module. That is, if the MSB is mapped to the LSB and the LSB is mapped to the MSB, then we can do the lane reversal on the TX to correct that. Uh, to discover it, each lane is assigned a lane ID that are given in table 18 and 19, and we'll cover that later. That how we send the lane numbers, and if we receive them in reverse order in most of the lanes, then we reverse the lanes. In addition to lane reversal, we also have redundant lanes. So if some of the lanes are not functional, we can discard them and move them out. So basically, this diagram shows that the different arrows shows that in which direction we can move the lanes. So for example, if there is a faulty lane, what we can do is that instead of we can forwarding using that lane, we can use the lane adjacent to it instead of that. So we have to move all, for example, if this was faulty, then we'll move it to 28, 28 will move to 27, and so on till this redundant lane. And this is done using these muxes which support not only this lane but also the ones from the neighboring one. So that can be done this way. Similarly, if there are two adjacent faulty lanes, we can move this towards the left side and this to the right side. So so using two extra redundant lanes, we can still have fully functional lane. There are some details to it. The algorithm is also discussed in the chapter, how to do that, but the main idea is this, so I'm not going into that detail because we won't most likely be implementing it ourselves. There are similar repair and remapping mechanism for clock, valid, and track lanes. Um, that I'm also skipping that because in that case also we can remap just like this. And in standard package we have instead of remapping, we don't have redundant lanes in standard package, but if some of the lanes are faulty, we can degrade into by 8 mode instead of by 16. uh, so we have data to clock training and test modes. We can use actually we can send a pattern from transmit die and receive it and compare it with the reference pattern and detect an error based on that. So that pattern can be generated using already known patterns using LFSRs. XOR here is used to do the comparison. We know that XOR gives a 1 if both are different. So, so it can be used to detect errors. So there are two kind of detections. One is having per lane error detection. We have a sticky bit on each lane, and if one of them fires, that means that we had an error in that lane. And also we have this, we can OR all the lanes and have a counter incremented whenever there is an error, so we can have an aggregate comparison based on that. Okay, So link when is link initialized and trained? So what are the triggers? So if a software writes one to the start UCI training bit in the UCI link control register, it will start training. If the another way is that adapter triggers link training on RDI interface, and the RDI state is reset, and there is a no up to active transition on the state request. So basically this is the way it is triggered. So if RDI is already in reset and we do a no up to active transition on the state request, then we do the training. So we come out of reset and we do the training. Sideband init pattern is observed on any sideband receiver. Uh, so basically two consecutive iterations of 64 UI clock pattern and 32 UI low means that the sideband init pattern is received. So basically we have following basic operations for link training. One is transmitter initiated data to clock point test. Then we have transmitter initiated data to clock I width sweep, that is used to have the to to identify the center of the eye, and similarly we have receiver initiated data to clock point training, and receiver initiated data to clock I width sweep training. So in all these trainings, there are some common kind of similar parameters that are used in all of the things. First is um, the clock sampling or phase control. So here we have options of eye-centered for center found by training, or left edge found by training, or right edge found by training. Another parameter is what pattern is used. So TX pattern generator setup, we have the pattern for data lanes, per lane ID pattern or data lanes that is defined in this section, or there is another wall train pattern, 4 ones followed by 4 zeros. So on the valid. So then we have a count setup, whether we are doing a continuous mode count or burst count. Uh, and then on the RX compare setup, maximum comparison, error threshold, or per lane or aggregate comparison. These are kind of the settings that we use. So, in the transmitter initiated data to clock point test, module setups the transmitter parameters. So, like shown here, sends TX initialized D to C point test requests. The receiver enables the pattern comparison circuits. Uh, Partner responds with TX init D2C point test response. So this is sent across the die to the other die, and this the partner is the other die that is responding with the response. So so our side of receiver is enabled for pattern comparison. Module we reset the LFSR on our TX and send LFSR clear error request. So the partner resets the LFSR, responds with the LFSR clear error response. Now we send the pattern, so using whatever setup we used here, and for the selected number of cycles, which is the kind of count setup. The partner performs the comparison based on the compare setup, and after that we request for the log results by D2C result request, and we get a response D2C result log. Uh, when we ask for results, the partner stops the comparison and respond with the logged results. So all these curly bracket things are the sideband messages that are exchanged between both dies. So module sends stops sending by the pattern, and this end tx init d2c point test request is sent, and when we get the response from the partner, this whole process ends. And at the end of this process, we enter the electrical idle state. So basically, we can say that these are the steps that Param set up. Then we exchange these request and response packets. So this is a common pattern that most of the time we exchange something request and followed by response, and request response, request response, request response. So we started the txnet d2c, we got a response, we cleared the LFSR and then send a request, and so we got a response. Then we send the pattern, and after that we send the result request and got a response, and we send an end request and end response, and then we move to idle. So, so similar pattern is repeated in other cases as well. So this was data to clock point as in data to clock I bit sweep. We again set up parameters, and now the message is the sideband message is different. In this case it's I sweep request and sweep response. Again we cleared the LFSR and send the patterns and then get the logs. But here what we do is, instead of just getting the log, we sweep phases to find the passing phase range for the I sweep. And again, in the end, we send the end request and end response, and we enter the end. On the receiver initiated data to clock point running, again we module enables the pattern comparison circuit, set up the receiver parameters, sends the RX init D2C requests. So earlier it was TX init D2C, now it's RX. So on the partner, the module should be idle. The partner responds with the response, and partner resets its LFSR, then sends a request that we clear our errors, previous errors, and so the R module resets the LFSR's prior results and send a response. Then the partner sends, because we are the receiver, so in this case, and we initiated the data to clock point running, so the partner will be sending the pattern. So the roles are kind of reversed in this case. So, so module performs a comparison and logs the results. Partner sends the count done request, and module stops comparison and response with count done response. And now we can use the log data, and then we can end it using end rx init d2c test request and get a response. And again, after that, we enter idle. Similar is the case with the receiver initiated data to clock I with sweep running. Again, so now the responsibilities are different, that we are the receiver, so we enable receiver and send the I sweep request and get a response. And then partner resets it LFSR and asks us to do that, and then partner sends the um, send and receive, and we compare the results, and we generate the results, and partner requests the results using results request and log, and partner basically sweeps to find the right phase range. And after that, partner sends the done with the results, and module sends an end signal, and we send an end response. So this done with results actually provides us with the phase range that is that can be used. Okay, so so this diagram shows basically two dies over the external link. So external and UCI links are permitted to come up independently, so they came up independently. This SB init, sideband init, and mainband init with local parameters and local data rate. This shows that. So then external bring up is done independently, and now we can send retimer messages, and then we have some messages exchanges based on which we initialize the protocol and do the so there can be multiple basically speed and width resolution iterations here, and after that we come out into an active state. uh, okay, so when we get a suitable configuration, we go to link in it, and after that we basically can send the data. So basically this is the state machine for link training. So reset state is basically when we come out of reset, we are in the reset state. Uh, so SB init stands for sideband initialization state machine, in which we initialize the sideband and repair it if needed. MB init stands for main band init, and it also repair if required. MB train is the training state machine in which we optimize the speed of operation and get to the highest speed. In the MB init, we go to the it is initialized at the lowest speed. Then we do MB train to get to the highest speed, and on the highest possible speed we initialize the link. The link in it is used to exchange adapter and link management messages, and then we become active, and now we can send and receive data. And from any stage we can go to power management state if required. Sorry, from the active state we can go to power management state if required. There are two kinds of power management states, L1 and L2, and also we can go to fire retrain for any reason that adapter may deem necessary, or we have some error in the file, and similarly when we get a fatal or non-fatal event, we can also go to train error state. So kind of from reset to active, we have this sequence of states: sideband init, mainband init, mainband train, link init, and active. And then we have a few other states like power management states, L1 and L2, and train error or fire retrain. So the reset, if I must stay in reset for a minimum of 4 milliseconds to allow PLLs to stabilize. The minimum conditions that are necessary for coming out of reset are power supplies are stable, sideband clock is available at 800 megahertz, main band and die-to-die adapter clocks are stable and available, and the slowest main band clock is set to the slowest rate, and SoC or firmware is not keeping the fine reset, and link training trigger has occurred. So so these are all the minimum conditions. So once we come out of reset, we go into sideband init. So in advanced package, we have redundant lanes. So in sideband init, if required, we might have to repair the link. So so here's the flow. Keep sending iterations of 64 UIs of clock and 64 UI low on both TX. Uh, so partner must sample a pattern on RX on incoming clock. The data clock receiver detection if two consecutive pattern in step one. So if we get two consecutive such patterns, so we say that data clock receiver detection is done. If partner detects the pattern on at least one, we stop sending after four more iterations. And now we can enable send receive message. If pattern not detected, we must continue to send the pattern for 1 millisecond and idle for 1 millisecond for 8 millisecond, and after 8 millisecond timeout will occur and will move to train error because nothing was detected. And if detection is successful or more on more than one combinations, so then we can pick a combination based on priority order. If in step 4 sideband was enabled, so we continue to send SB init out of reset sideband message on both until it detects the same message on RX or it times out. So if out of reset is successful on RX, we stop sending the sideband messages. Before sending any further messages, both module and partner must apply data clock assignment based on whatever info was sent in the SB init out of reset message. Any further messages now can be sent, so the sideband is basically up. Module send the sideband init done request and waits partner response with done response, and when that response is when we get that response, we exit to main band init. For a standard package, the steps are similar and actually a bit simpler, so they are skipped here that can be read from the spec. For main band in it, there are multiple substrates. We start with the mbinit.param. Basically, it performs parameter exchange of parameters required to set up minimum negotiated speed and other file settings. Then we have we perform any calibrations that are needed, for example, duty cycle correction or receiver offset and VREF calibrations. Then we repair clock if required. So that I already told that in advanced packages package we have redundant clock and track lanes. And then we repair valid if required, and then we do the lane reversal if required, and then we repair the main band if required, and from there we move to train. So let's look at it one by one. So for parameters, we send parameters configuration request and we get a response. So the configuration request basically has module ID, the clock phase, clock mode, whether it's in continuous mode or strobe mode, voltage swing, and max link speed. Then we move to calibration to perform any calibrations if needed. So for that we send calibration done request and done response. After the calibrations, we send the done request and done response. In the repair clock mode, we basically send repair clock init request and get a response. send 128 iterations of clock repair pattern, and on T clock P only, and we detect it on all of the receivers for clock L, clock NL, PL, NL, and then track and track redundant, clock redundant. So if in the 128 iterations we get at least 16 consecutive iterations, we consider it a success. And so then we get the result request and get results back. If we get on our clock PL only, that means no repair is needed. But if the detection is successful on any two, then it means that there was an electrical short, and if no detection, then repair is needed. Uh, so we repeat the steps for these T, clock, and L, and rest of the signals. If required, we apply repairs, and for that we have apply repair requests with repair info, and repair is applied as we discussed earlier, that we move the lanes, and after that we get apply repair response. uh, So if it's unrepairable, so if we, for example, repair needed on any two of these, then we go to train error. So that means it's irreparable. So if repair is applied, then we check the repair, and by using check repair init request and response, and again we send the pattern uh, and detect on all the lanes, and if that is received on one of them, then we know that it's successful. And then we see the results. So if T clock PL, we transmit on this, and we received on R clock PL, that means it's successful. If it's not successful, we go to train error. And we repeat the same process for rest of the clock and track pins. So if successful and no repair is required, then we send done request and done response, and from repair clock we move to repair valid. For standard package, there are similar steps, but there is no repair needed. For repair valid, the steps are again pretty similar, but the messages are different. So instead of repair clock, we have repair valid init request and response. And again, the pattern is different. We send valid train, 4 1s and 4 0s, and detect on the receive side. And if it is successful, then no repair is needed. If we have detection on both, then it's unrepairable. If we don't detect anything, that means we can move to the redundant lane if it's an advanced package. uh, so so we repeat the same steps for TRD valid L, and if it is unsuccessful, it's not available for redundant. This RD stands for redundant. So if the redundant lane is available, then we can apply repair. If it's not, then we can't. So if it's available, we apply the repair. If it's successful, we do the same steps to check it. And if it is successful, we just do the done and done response handshake and exit to repair main band. In all the cases, if the repair is unsuccessful, we move to train error. For standard package, it's similar, but it results in degrade if there is an error. So it's skipped here. For main band reversal, we send the lane ID pattern on a specific lane. So based on that, so basically we send MB init, reverse init and response, and clear the logs and 128 iterations of per lane ID on all lanes. If at least 16 consecutive iterations, we get the correct lane ID, that means we are it's okay. But otherwise it's not. We then get the results. If majority shows success, we don't do lane reversal. If majority is unsuccessful, we do the lane reversal. And after that, if majority shows success, reversal is preserved. And if after reversal still we have majority unsuccessful, then we move to train error. Success means that we do the done handshake and exit to repair main band. In repair main band, basically module sets the clock phase to the center of data UI for main band, and for again that we send request and response packet on the sideband, and then we do the transmitter initiated data to clock point training, and that we already discussed basically. So 128 iterations of continuous mode per lane ID pattern, and if we have 16 consecutive iterations, then we have success. Module then receives the pass fail information. If repair required and resources are available, then we apply the repair using these messages, and then we repeat the above stage. If failures are greater than capability, then we exit to train error. If repair is successful, then we do the repair and request and response. So this is the same repair that we discussed earlier. If there are multiple lanes in error, we can move them towards the sides. In standard package, instead of repair, we do the degrade. So here, this table shows the degrade possible. We can either have 0 to 7 lanes available, or 8 to 15, or all of them. So after MB init, we move to MB train. So MB train is in itself another kind of long state, long substates state machine. So the typical template that we kind of already have seen is that the substate state dot substate start request and start response is typically the message we exchange. So request is sent from one module and response is received from the other one. And then we have some iterations of pattern sent, and if we have a threshold of cross, then we can say it's a success, and then we can take actions based on the results. For example, repair or sweep or some setting. And if action taken, then we generally repeat to validate it. And if still we have error, then we go to the error state. And if we have success, then we go to the next state. So it's a sequential kind of a flow. So we know that which state we need to go to. And also when after that we actually do the end request and end response. So this is the general template for all of the stages. But values of these things are different. For example, for val reference, receiver reference voltage is optimized. So message in this case is val vref. So this is the name of the state. So we exchange state dot val vref start request and response, and we test the receiver initiated data to clock point training or IVET sweeps, and val train pattern is used. And if the error is less than a programmable threshold, then we consider it a success. And what actions we do is that we step through all the vref settings and see which one performs best. So after val ref, we do data vref. uh, Here we receiver reference voltage is optimized to sample incoming data. So in this case, instead of val vref, we have this message. Again, same test, but 4K, the pattern is different. Instead of val train, 4K unit interval of continuous mode LFSR pattern is sent. And again, another threshold is used for this. And we step through all VF settings to find out which one performs best. The speed idle is an electrical idle state to allow frequency change. So if we can come here from different sources. If we're coming from val vref, we transition to highest common speed. But if we are coming from fire train or link speed, then we go to the next lower data rate. So the TX self-cat here module calibrates circuit parameters independent of partner. And here we after that we send a done request and done response. RX clock calibrates the clock receive path. Uh, so clock calibration start request, partner starts sending the forwarded clock and sends the response. After required calibration, if any, we send done request. Uh, the val train center ensures that valid is functional. So valid to clock training is performed before data lane training. So the message in this case is val train center, and transmitter initiated IVET sweep or other tests, and we do 128 val train, and again we check whether the errors are less than a threshold. The action we do here is we use received result logs to assess valid functionality and margins. um, Optionally, we optimize VREF for sampling incoming valid as well. So this is similar to what we did for data earlier. And we adjust VREF on valid receiver, basically by going through all the combinations of it. In data train center, again, we perform full data to clock training. So this is the message. TX initiated I-bit sweep or one or more point tests, and we send the LFSR patterns and see if the errors are less than a threshold. Uh, so basically, the action is to set clock phase to sample that I at optimal point to maximize the I margin. So, so that's so when the maximum margin is maximum, we'll have least errors. So we optionally optimize VREF on data receivers as well. So this is again similar, but earlier we did it for valid, now we are doing for data. RX DSkew basically is used for lane DSkew on RX to improve timing margins. Uh, so basically again the message is this, and sideband message is this, and again we do receiver initiated divert sweeps and use the LFSR pattern to do that. MB train data train center 2 basically recenter clock to aggregate data in case of DSkew, similar to data center 1 with message, only the message is different. For link speed state, we send this link speed start request and response point test with final clock sampling phase calculated, and again the 4K unit interval of continuous mode LFSR pattern is sent and successful if the count is less than a threshold. Uh, In single module instantiation, if errors, then set TX to idle and send link speed error request. Partner completes step 1 and 2, enters idle on RX and sends an error response. If no lanes in error, repair or width degrade. If it's advanced package, we repair. Uh, Sorry, no, probably said no lanes in error, but number of lanes in error is there. So if there are multiple lanes in error, so then we either repair or degrade. If repairable or degradable, so we do the link speed exit to repair request, and partner enters repair in that case. So here we go to the repair state and exit to repair. If unrepairable, then we do the speed degrade, and in that case it's instead of repair it's speed degrade request, and so we exit to speed idle. So this second arrow coming from here goes to speed idle. So in that case we just move to next speed and do all the steps again and again. If it doesn't match, then we go to next lower speed and so on. So if we go to speed degrade, then we ignore outstanding repair requests. If no errors, set clock phase to maximize I margin, and then we send the done request and done response. And if phi and retrain is not set, then we can proceed to link init. If it is set, change runtime control testing control register, and and if there is no change, then we find retrain. We can clear the find retrain variable, and we can proceed to link init. For multi-module instantiation, after step 2, module reports results to multi-module file logic and waits for resolution. Then then we follow the rules in this section and provide action to each module. So actions can be exit to link init or exit to speed idle. So basically the same actions that we already saw, and or either exit to repair. Uh, if no errors and it is a retimer, don't send done request until the target link speed and width of remote resolves to current link and speed. And while resolving target link speed and width, we send done response with stall encoding every 4 milliseconds so that it doesn't time out. But retimer needs to also make sure that it's not perpetual. uh, so if local UCI link speed or width is greater than remote, then we send the done response without the stall encoding. Must be treated as error condition and perform step 4 or 5 with repair or speed degrade to have the same link speed. Both TX and RX, after all this, both TX and RX are now enabled and idle, and both devices exit to link init. So in repair, we can enter from fire retrain or from the link speed. So for repair, we just do the repair init request and response. If it is repairable, we apply repair on TX and send the apply repair request, and partner applies repair and sends the response, and then we can send end and end response and exit to self gap state. Similar for standard package, but it degrades instead of repair. Okay, so we go to link init after this all this training detail. So in link init, it's used to allow D2D adapter to complete initial link management before entering active state on RDI. So we'll see details in later section. Once RDI is in active state, fire clear start UCI link training button, UCI control register, and basically we move to active state. In active state, fire init is complete, RDI is inactive, packets from upper layers now can be exchanged between the two dies. All data is now scrambled. Fire retrain can be done for a number of reasons. If adapter uh, deems it necessary for any reason, or if PHY detected a valid framing error or report or remote die requested for a PHY retrain, or if we have a change in runtime link testing control register during link speed, or a variable fire retrain must be set when entering the fire retrain, and that is cleared. We already saw it when we move to active. So from fire retrain to MB train, we have already seen that we can we can either go to repair or self cal or speed idle from fire retrain. And so table 26 gives us test status register based on retrain encoding. So so this is the resolution of based on start bit, if repair is needed or not needed, which state we should go to. So these tables are basically used for resolving which state we should go to based on the information from the remote die and local die. Uh, uh, so now we can go to the adapter initiated firetrain module. If module receives a return request from local adapter, this is the first step. Then module completes the stall ACK handshake on the RDI. More details on it later. And then we send an init request. The partner also does the handshake on its side, and it sends the response, and module transitions its RDI to retrain, and we send the retrain start request with retrain encoding. Basically the runtime control register except the start bit, and partner compares it with the local encoding. If it's same, it sends the response. If it does not match, then it resolves according to the tables we saw in the previous slide, and then sends the retrain response. And after that, we exit to the corresponding training state. Fire initiated fire retrain is similar, except the cause is valid framing error instead of the first step. And remote die requested fire retrain is also similar, but from partner's perspective at 2 instead of adapter initiated. It's the other side's adapter initiated kind of. Fire train from link speed similar, but starts at 0.5 because it's not we don't need to do the stall act handshakes. Train error is a transitional state due to any fatal or non-fatal error events that occur before going back to reset. Um, for anything other than sideband init means handshake, and basically train error entry request, entry response, and response or timeout means that we go to train error. L1 and L2 are power management states, and so basically lower power than dynamic clock getting inactive. So entered when RDI transitions to PM state. Power saving features are implementation specific. So local adapter requests active on RDI or remote link partner requests L1 exit. And that means that phi must exit to speed.idle. So so basically L1 exit will take us to main band train, and specifically to speed idle state that we saw in the previous slide, because here ambi-train substrates are not shown. But the L2 exits to reset states. So that's the main point here. And the last thing is that track signal can be used for runtime. So this is not related to state machine as such, but track signal is used for by the RX for periodic runtime calibration in active. So module enables track buffers by using this message on, and partner sends the track pattern net response, enables track TX. TX starts sending the pattern, RX performs calibration and sends the done request and done response, and based on that we can actually track the signals. So track is a signal parallel to track signal will be actually discussed in electrical sublayer, and it's an extra signal basically used for um, adjustments based on temperature or etc. Skipping some of the details about multi-module links. So now next move to electrical layer, chapter of the spec. So we already discussed the signals between the dies. So we have two kinds of packages in 16. In the standard package, we have 16 data lanes. For advanced package, we have 64 lanes. We have two clocks, one valid, one track signal, and same signals from this side's TX to this side RX. And for sideband 2, we have sideband clock and data signals. Um, so the transmitter, this is the diagram of the transmitter. It has data, FIFO, and serializer, and data plus valid can be considered as a kind of a data lane, which having in fact valid framing. And for clock, we have two phases and an extra track signal, which is used for to compensate for slow changing variables as voltage or temperature. The TX sends a copy of phase 1 of clock signal when requested over sideband. On the RX side, these signals are connected here, and we have D skew and uh, and FIFO outputs the data to the output layer. I'm skipping some lower level details here like electrical parameters, termination, then equalization like de-emphasis on TX or CTLE on RX, and then there are some bump maps given in this chapter. But since we'll be working on the upper layers, so I'm skipping it here. So this shows the clocking architecture of PLLs and DLLs, and each module supports two-phase forwarded clocks, and receiver must provide match delays between the clock distribution and data valid RX pass. Phase adjustments are performed on PX. Link running is required to set the position of phase adjustment to maximize link margin. Per lane, DSkew must be supported in DX at high data rates, and so basically specification supports quarter rate clock frequencies at very high data rates, and the forwarded clock must support quadrature phases. Some training state need electrical idles. Electrical idle is when there is no data transmission on the main band. So, for example, in case of unterminated advanced package and unterminated standard package, data lane transmitter must hold a last transmitted UI. So basically, we have this transmission, then we have a post-amble 16 unit intervals, and after that, this phase is when we have no transmission on the main band, so clock is gated and data is parked on the last value. And a valid lane must be data must be hold the last UI. Valid must be held low. Clock level in idle state after this post-amble requirement must alternate between high and low during consecutive clock getting events. Means that if in this cycle it's high, then in other next clock getting event it should be low. So before coming up, clock must drive a differential low for at least one UI or a maximum of 8 UI before normal operation. So here here is the normal operation. So before that, clock must be low for 1 to 8 UI. So it remained low here. For terminated case in standard package, data lanes must send last UI for at least one UI or up to 8 UIs. So up to 8 UIs, we have 1 to 8 UIs, and then we have this high impedance state. So this was the 8 UIs. This could be 1 to 8, and after that we have this high impedance state for data. Valid lanes must be low. Clock must alternate between high and low, just like previous case. TX must precondition data lanes to a 0 or 1, and clock must drive a differential low for at least one UI or up to a maximum of 8. So this is also the similar thing, that before coming back up, it should remain 0 from 1 to 0 UI, and for data lanes it should be preconditioned to either 0 or 1. Now let's move to the sideband chapter of the UCIe spec. Um, so basically sidebands is for each module we have a clock and a data pin that can be used for sideband messages. So in the last section about the state machines, we saw a lot of request response sideband messages. So in this chapter we'll be going into a little bit of detail about that. So basically sideband provides a back channel for link training and sideband access of registers of partner, also used for link management packets and parameter exchanges. Same protocol is also used for local die sideband accesses over FDI and RDI. So PHY is responsible for framing and transporting sideband packets. Direct sideband access to remote can originate from either adapter or physical layer, but not from protocol layer. Adapter forwards a remote sideband access over RDI to PHY, and includes register access and completions or messages. The protocol layer has indirect access to remote edges using sideband mailbox mechanism. So protocol layer can read write on the adapter layers edges, which can trigger basically the a sideband message to the remote side. So mailbox register reside in adapter. Adapter initiates remote reg access request when it receives an access trigger for mailbox register over the FDI. So for multi-protocol stacks, adapter to track which stack send request and route the completion to that appropriate stack. And protocol is allowed only indirect access, but direct access to local registers. So only register access requests and completions are permitted on FDI interface. There is an 8 millisecond timeout, so a stall encoding can be used for a timer to reset the timer after, let's say, every 4 millisecond. But it must not stall indefinitely, and after reasonable number of attempts, it should escalate a link down. So registers can be fragmented into different layers. So we can do hierarchical decoding in that case. So if a bit is not physically reside in a given layer, it's implemented as read only and tied to 0. So the next layer will fill that. So so there are different kind of packet types. First is configuration or memory map read writes, which can be 32 bits or 64 bit. Messages without data, for link management or vendor defined packets, they don't have any payload. Message with data are for parameter exchange, link training related, or vendor defined. They have 64 bit data, and each packet carries 5-bit opcode, 3-bit source ID, and 3-bit destination ID. So this is the encoding of opcode, the 5-bit opcode. So different bits mean different things. So these encoding means either it's a 32-bit memory read, or 32-bit memory write, or 32-bit configuration read or write, or a 64-bit variant of the same thing, or whether it's a completion without data or completion with data, 32-bit or 64-bit, whether it's a message without data or message with data. So for FDI sideband, so source ID and destination encodings are this. So for source can be stack 0 protocol layer, stack 1 protocol layer. Destination could be die-to-die adapter or file layer. So for RDI sideband, so for FDI means that this is coming from protocol. So for RDI means it's coming from adapter. So adapter can forward this packet to the PHY as well. So it could be either a protocol layer 0, stack 0 protocol layer, stack 1 protocol layer, or it could be initiated by adapter itself. So here we have this extra encoding, and again it could be a local data terminated request or a remote data terminated request. So we could be reading FIS registers or remote dies registers. So this bit is set accordingly, and destination can be for local die it's physical layer, for remote die it's reserved, uh, for for completions it one means die-to-die adapter, and here for remote die terminated messages it could be either adapter message or a file layer message. So so here we can see the 64 bits of uh, register access requests. So so different fields are further elaborated in this table. CP is control parity, DP is data parity, both are even parities. CR is a credit return for credit sideband messages. Address is the address of the register, and byte enables are byte enables. EP is used for poisoning. Tag is a 5-bit field generated by requester and should be unique for all outstanding requests. Data is a payload. For example, if it's a write request, then we need data with that. So the address field is further divided is like this: for memory read writes, for configuration read writes. So for memory read writes we have 20 bits offset, and then RL3 down to 0, and which has following encoding: register locator 0 to register locator 2. And if the encoding is F, it means that access for protocol specific MMIO registers that are shadowed in the adapter. For example, MUX are MUX registers defined in CXL spec. uh, for configuration reads, we can go to 0 means that UCI link DevSec, and F means access for protocol specific configuration registers that are shadowed in the adapter. For example, RMUX registers in the CXL. So this was requests. For completions, it's a similar thing except that we have status here, And status is encoded in this way that it could be a successful completion or unsupported request or completed abort or stall. These are now register access and completions. After that, we have messages without data. So message encoding means these fields. So message code or message info or subcode. Uh, these mappings are given in this chapter. We have a big table of that. So basically, nop.crd means end-to-end credit return. Link management RDI.static coordinates RDI state transitions. Similarly, adapter 0.static coordinates adapter state machines, adapter 0 state stack 0 state machines, and similarly adapter 1 means stack 1, and parity feature coordinates parity insertion enable, error messages, reports and escalation for escalation. So here I just copied initial part of table 53 with the message code, subcode, and message info encoding. So message code, message info, and message subcode, that's there in the data. So here you can see that link management.rdi.request.active or .request.l1 or l2. So these are all the curly bracket messages that we saw in the state machine of link bring up as well. So for those cases, message code and message subcode fields are like this. So this is kind of the actual bits that will be transferred if we want to send that sideband message. So similarly, this is adapter 0 request active. Uh, so here it was RDI, but here it is adapter 0 request active and adapter 0 request L1 and so on. Table 54 gives message encoding for link training state machines. There are such 132 such messages. So it's a big table, but we have seen most of those training states. For table 55 gives the message encoding for messages with data. So in this case, we have these 64-bit data as well, but again, we have same message code and info and subcode fields. So for example, in case of adapter capability message that we saw in the initial parameter exchange, so this is the encoding of different bits corresponding to whether which mode it is and which type of let format it is. And okay, so for flow control, each TX design time parameter, we have a flow control is managed using credits. So every TX RX pair has independent credit loop, and we can have at max 32 credits. And TX transmits only when credits are available. So for the register access, TX must not check for credits before sending register access completions. For completions, we don't have any credits, so all completions must sync. And but the register accesses need credits. Uh, so for RDI and FDI, we have dedicated sideband signals for credit return. All RX must check for parity errors, and it's mapped to uncorrectable internal errors and results in link error state. Uh, Our UCI sideband link between dies, if bit error is rate is less than 10 to the power minus 27, we don't need any retry on sideband, and so Rx of sideband checks parity, and that's mapped to fatal, uninterruptible, uncorrectable internal error. So basically, deadlock is avoided by ensuring that there is sufficient space at Rx to sync all possible outstanding requests. So, uh, sideband access for partners, adapter file register only via indirect mailbox mechanism. And outstanding transactions are limited to 4 at a time. 5 and adapter must have this capacity that it could sync at least 4 register accesses from the remote side. Completions do not consume a credit and must also always sync. Credit counters for register access request are initialized to 4 whenever we are in reset. But we can send an extra n minus 4 credit return to partner if implementation is capable of syncing n requests where n is configurable. For all other messages except vendor defined messages must always sync and make forward progress and not block any messages on sideband interface. All link management message requests have an associated response, and source of these messages must only have one outstanding request at a time. There must be a vendor defined cap for outstanding messages. So it's not defined, but there has to be some cap. Let's move to configuration and params chapter of the spec. So basically, the key goal of UCI is to leverage all the software infrastructure for PCI and CXL while still defining the interface in extensible way. Software view of protocol is basically consistent with the associated protocol. For example, a downstream port for supporting CXL will appear to software as a root port with CXL DevSec capability and relevant PCI capabilities. But down port for supporting PCI only will appear to software as root port with relevant PCI capabilities only. Streaming protocol is implementation specific. Upstream port that connects to a UCI root port can be a PCI Express endpoint or switch or CXL2 or above compliant endpoint devices or a CXL switch. So this allows UCI to be fully backward compatible. Software discovery, how it's done is basically so in host we have CIRB, host specific register block, and its base address is basically enumerated using early discovery table CIDT, which has another spec of its own. So from there we can get to CIRB, which has this DevSec capability for the UCIe. So association of a UCI link to one or more root ports is described in CIDT. So that allows UCI aware software to understand the potential shared nature. In endpoints, the dev0 and function0 of the device carries this DevSec capability. In switch upstream port as well, the dev0 function0 of the upstream port carries this DevSec capability. And in the downstream port, again DevSec of the switch USB carrying one or more. So for downstream port, it's CISRB that carries this DevSec functionality. So basically, UCI has defined two DevSec capabilities, one UCI link DevSec and CISRB DevSec, and three other MMIO mapped reg blocks are defined. So this table actually shows that for root port where we could find those DevSec and regis block basically, and for root port, for switch, upstream port, downstream port, endpoints, and retimers, from where we can find these. This UCI link DevSec basically are registers that define the basic UCI interface related dates. The data or PHY register block registers that define lower level functionality for PHY interface. Similarly, for test and compliance registers for test and compliance, and implementation specific register blocks are for vendor specific registers. So UCI link DevSec capability is located in CIRB for host root ports, and in CISRB for switch downstream ports. This region is defined at a static location on host side, and its size is enumerated in CIDT structure. There is a unique CIRB base address for each UCI link in the host. CISRB base address provides CISRB DevSec. This is part of bar region of switch dev0 function 0 USB. In case of multiple CISRB DevSec capabilities in USB, a given UCI link can only be described in one of those. Configuration space regis are accessed using configuration read writes. Reg blocks are in memmap region, accessed using standard memory read writes. So the retimer regis are not directly accessible from host software. They can be accessed only via window mechanism over sideband interface. Hence the term SBIO here in the table. The window mechanism is available via root port, DSP, downstream port, UCI link, DevSec capability to access the UCI retimer regis on the retimer closest to the host. For accessing the registers on the far end retimer, the same window mechanism is also available in UCI link DevSec capability. For debug and runtime link health monitoring, the software can access UCI related registers in any partner die on the sideband interface using the same window mechanism. So this slide shows the software view example with root ports and endpoints. So here we have a host with two UCI downstreams links that each carry traffic for two root ports. So here this is the UCI DevSec in the dev0 function 0 in the endpoint, and connected to UCI1 and UCI 0 root ports. And here this is the host defined base address of CIRB, and from there you can go to the UCI, for example, implementation specific header and comp test header and so on. And same for the second case. This is software view with switch and endpoints, and here we have switch with two UCI link on its downstream. So we have a switch with two UCI links. So here in green we have one, and in red we have another DefSec and related reg blocks. This is software view of UCI endpoint, and here we can from the bar and reg locator we can go to the UCI implementation specific details. So this is the DefSec defined for UCI. So we have here on the right we can see that which one applies to which. Some of the fields are only required for endpoints, some for upstream ports, some for retimers, some for root ports, and some for downstream ports. So first thing is the extended capability header. So the header has capability ID with a fixed value here, a value for PCIe Express DefSec capability, and then we have Rivian ID. So then we have next capability offset, which is for UCI link DefSec and CIRBs. This is set to point to MSI capability with the associated link. For UCI link DefSec and CI SRB, it is set to the point to the UCI link DefSec capability of next UCI link associated with the downstream port. And the last UCI link DefSec capability will set this to 0. So there can be multiple offsets like that. So the designated vendor specific header has basically a Rivian ID, and that's the variant of DefSec structure. The Rivian ID is incremented whenever structure is incremented to add more functionality. Backward compatibility shall be maintained. So for all values of n DefSec Rivian ID n+1 structure may extend Rivian ID by replacing some of the reserved fields. The capability descriptor field basically describes the capability. So we have number of register locators, sideband mailbox registers, whether they're present or not, number of switch DSPs associated with this UCI link. So all this information is in the descriptor. The UCI link capability tells us about the capability of the link, whether raw mode is supported or not, what is the maximum link speed, maximum link width, maximum link speed, whether it is a retimer or not, whether multi-stack capable or not, what kind of package it is. So the UCI link control is used to control link. If we want to enable raw mode, we can use raw mode enable. If we want to enable multiple stacks, we can do that. And similarly, we can set the target link width, etc. We can also set the target link speed. We can start link training. We can retrain the UCI link, and we can enable, disable the clock gating. So these are kind of the controls, and the status things are whether raw mode is enabled, whether multiple stacks are enabled, what is the current link width and speed, and whether link is up or down. Similarly, link training, whether currently link is training or retraining, whether its status changed. Hardware autonomous UCI autonomously change link width or speed to correct link reliability related issues. So if something is changed by UCI, then we get this bit set. And similarly, correctable and uncorrectable non-fatal errors for that. Okay, so similarly, for link event notification control, we have link status changed, UCI linked event uh, interrupt enable. 0 means reporting of this why interrupt is not enabled. 1 means enabled. Hardware autonomous bandwidth changed. So whether it is interruptible or not, and link event notification interrupt, what should be the interrupt number, and similarly error notification control has a bunch of notifications for whether correctable errors protocol reporting should be enabled or not, whether on the protocol layer. Similarly, correctable error detected link error interrupt is enabled or not. Similarly, uncorrectable errors for protocol and link and so on. There's a bunch of things that could be enabled. Uh, then we have register locators, low and high. So these are register block identifiers, block offsets, and then we have sideband mailbox index. So for we have high and low fields for that. Um, here we have opcodes for whether it's memory read, write, byte enables, address, and and then we have this write data. So for sideband, and then we have this read write trigger bit that when this bit is written to 1 from a value of 0, the mailbox generates traffic on the sideband interface. So if we want to generate traffic on the sideband interface, we set rest of the bits, and when we write to this bit, it will trigger the, the sideband traffic. The status field shows whether there was a success, or whether it was an unsupported request or completed abort. So this shows the status of the mailbox request. uh, So for host side UCI links, we have segment number, bus number, function number, etc. And these are basically requester ID fields as shown here. And of associated port numbers of the first switch DSP associated with the UCI is given in the port number link, and port number of the second switch is given in the next one, and so on. So the switch register block CISRB capability, DEFSA capability can only be present in config space of upstream port of the switch. So again, it has Rivian ID and capabilities and vendor specific header and base address registers, etc. There are two DefSec capabilities, and then there were register blocks. So one of them was fire register block. It's again a bunch of registers with lower level details of file. So I'm just naming the registers here. So there is a block header, then and uncorrectable error status register, and mask registers, and severity registers, correctable error status and masks, and header log 1, 2, and error and link testing control register, runtime link testing, parity log 1, 2, 3, and adapter capability log, finalized capability log, CXL capability and finalized capability log, PHY capability, PHY control, PHY status, PHY implementation and debug training setup, and current lane map modules of the modules and error logs. So these are the bunch of registers that I haven't put for brevity, but they contain lower level details of the file that we discussed in various subsections before this. Test and compliance register block is not defined in this spec, and implementation specific register block should carry the same header at 00 with vendor ID and refs, maximum length 1 MB, 4, it should be 4 KB multiple. Now let's discuss the interface definition section, chapter of the UCI spec. So it's divided into two parts. First is the RDI interface and second is FDI interface. So as discussed earlier, the RDI interface is the interface with the PHY. So there can be multiple modules in the PHY, but the details of multiple modules are abstracted out using multi-module PHY logic. So from the die adapter layer, it's always a single interface. So here is the signal list, but before going to the signal list, the convention is that PL underscore statics refers to the signals coming from PHY, and LP underscore static means the signals terminating at PHY. Um, Everything is running on a synchronous clock on the RDI as well as on the FDI sides. So clock is common. So data is accepted when um, PL T ready LP valid. So this is data from adapter to PHY. So for adapter to PHY we have LP valid and LPI ready signals from the adapter, and we have a ready signal from the PHY side as well. And on if all of them are asserted at the rising edge of L clock, then data is accepted. So here, except the credit signals, these are the same signals that we discussed, and this is the data in n number of bytes. The LPD timer credit signal is basically the credit signal to return credits. On the opposite side, if we want to send data from PHY to adapter, we have valid data, and we also have credits for that. But here we don't have a ready signal from adapter side, so adapter must always sync the data. Uh, if adapter wants to request a state change, we have state request signal. We do have a link error signal, although it can be established from the state status as well, that we'll see later. But for immediate action, we have an independent signal as well. So the state status indicates the current state. In band present is an important signal. It shows that the PHY is active and it has finished running. So other than that, there are a bunch of error signals showing different kinds of errors, and PHY in recenter is showing that PHY is in train or retrain mode. The stall request is used to stall by the PHY to request adapter to stall the flits from the top. Its response is stall ACK. So PHY will stop sending flits and it will insert stall ACK. Speed mode and link configuration show the current speed mode and current link configuration. The clock request and clock ACK are used to ask the adapter to remove the clock gating and start sending the clock. And Basically this should not be on L clock domain, so that because L clock would be disabled when we request that, and the response is on L clock domain, so the adapter will enable the clock and send the clock ACK signal. Uh, the flip side is that if adapter wants the fire to remove the clock gating, it will send the LP wake request, and fire will remove the clock gating and send a PL wake ACK. In addition to that, these are sideband signals with a valid and the configuration and credit signals from both sides. So this is the complete signal list for the RDI. So we have these handshakes of wake up request ACK and clock request and ACK. So the main idea is that first wake signal should go up, and in response the wake ACK should go up. There should be at least one cycle bubble in between, and the wake request must deassert first, and then the ACK should deassert. So there are a bunch of rules that I'll not go into the detail, but these are to ensure that in different scenarios this is ensured. So I'll just skip those because that can be read from the spec. In this chapter, there are a bunch of rules that can be read from the spec, because they every rule has a different meaning, so not very good for probably to be covered in the slides. So I've just written down a few of those, but and there are, after the diagrams, there are some other rules as well that I have skipped. There is a similar clock request, and just like wake request, we have clock request and ACK handshake. So I've just added diagram of just one. So as I said earlier, that we'll have first clock request, and then clock will be enabled and we'll have an ACK, and then request will go down first, and then after that we'll get PL. The ACK will go down. There's some extra rules that again I'm skipping here, but this is important that this PL in-band present signal shows that we are inactive, and this is kind of a level trigger signal that it will remain active till the end of till we go into an error or reset state. So, so these rules can be read from the slide later on. Okay, so this is the state machine. So from reset, we can go to active state, and from active, we can go to L1 or L2 power management states, or retrain state if required. And also, we can go to link error, disable, or link reset state from any of the states, almost any of the states. So this is the flow of RDI bring up. So till here we have already discussed this kind of that each die will come up independently, then sideband will turn up, and then there will be training in the main band. So after that, when we get this PL inband present signal, so that means that we are inactive, phi is active. So adapter exits clock gating. So we have this the clock and wake handshakes, and after that it sends an active request. Uh, and same thing goes on the other die as well. So as soon as it goes to active, it sends an active request. When Fire receives the active request, it sends a request to the remote side, and the remote side, after becoming active, sends a response. And same thing goes here, that after giving a request on the RDI, if it has already received an active request, it will send a response, and both will adapters and will, after getting the responses, respective responses, both adapters can go to active state. PI will send an active signal to adapter, and after that we can start can start the signed band message exchange. So this was the RDI bring up flow. This is now the PM entry flow if we want to go into power management state. So if both sides are active, we get a request from one side of transitioning to L1. Phi will then before going into that, adapter must ensure that all LSMs are moved to PM, and after that we get Phi will send a sideband message of L1 request to other side. The other side should wait for 1 microsecond to see that if it gets an L1 response from adapter. If it does, it will send a request as well as response to the other side. After getting the response, the other side will go into PM, and it will also send a response here, and it will also go into power management state. So both sides will go to power management state after having a request and response handshake on both sides. So coming out of PM, sorry, no, it's not coming out of, it's an aborted PM request. So if we don't get a response within 1 microsecond, then the file will respond with PM NAC. So that means that this side that was going to PM state will come out of PM state into active state again. It can retry it after 2 microseconds. Uh, this is the PM exit flow. So in PM exit, let's say we are in L1 state, and then one of the side requests an active. We get a sideband message that sends a request for active, and the other side will go to retrain and become active. And on the RDI will send the response immediately, and will also, after becoming active, we send a request for active to the other side, and it will go into retrain then, and then it will become and it will send the response and become active after retrain. So both sides finally become active. The second part of this section was the FDI interface. So FDI interface is between protocol layer and data adapter layer. So in protocol layer, we have these options of CXL IO or cache mem, and we can also have multiple protocols having muxing between them. Uh, so again, the for the FDI signals as well, we have same convention. That PL underscore steric means that from the that signal is from the lower layer to upper layer. So it's PL doesn't stand for physical layer here, or not, neither protocol layer. It means that from adapter to protocol, and LP underscore steric means from protocol to adapter. So basically, this the same convention in terms of uh, from lower to higher level protocol, or higher to lower level protocol is used. This is used because the because RDI signals are a proper subset of FDI. So all the signals that we saw earlier are there in the FDI as well. But in the FDI, we have some extra signals, and that will be discussed here. So first of all, we have DLLP signals on both sides. So we have DLLP plus valid signal. There is a signal for optimized update FC, which I don't understand properly. And Then we have signals signifying what is the negotiated protocol and for what is the format, and a valid signal to show that these two values are actually valid. Uh, So, in addition to that, we have a request, active request, and active status signal. So, if we want to request protocol layer to get ready for RX, we use that signal, and the response is active status. Um, Additionally, we have indication that phi or RDI is in L1 or L2. I think there is a typo here. It should be L2. Um, and if there is a no offlet, we have this no offlet signal which can skip the retry buffer. It's asserted on the last transfer. And we have a corrupt CRC signal which is used for viral containment. There is a flat cancel signal that is asserted one cycle after the last chunk to cancel a flat. And additionally, we already have the signals that were already there, which I'm just reproducing here again for completion. So these were the signals that we already discussed. In RDI, these are all there, but we have some additional signals. This state machine for FDI interface is also pretty similar. So we have reset, active, and L1 and L2 states. So for FDI bring up, we see that when in-band present goes from 0 to 1. So protocol layer exits clock gating and gives active request. So so from here we get an active request, and that is sent from adapter to phi, and the phi will send that request to the other side, and there will get a request, and when the status changes in the on the protocol. So this active and status request and status were the extra signals that were added. So in the protocol layer, it will transition from the status will transition from 0 to 1, and after that we send a response to the other side, and also will send an active request to the other side, and the other side will also respond accordingly. And when both sides do that, both sides adapters TX opens their TX, and now they can be used for sending and receiving. If we have mux exists, then we have some extra packets on the main band that we already discussed, that ALMP packets to change the, the VLSMs as well. For PM entry, for CXL and PCI protocol, one die requests to go into L1 or L2. We do the stall and request handshake, and after that we send the request to the other side. Adapter waits for it for 1 microsecond, and if it gets a request from its protocol layer, it will send a response, and both sides will enter PM state. But for streaming protocol, we have to do the handshake from both sides. So we get an L1 request from here, we get a response, but the other side also sends a request and also gets a response, and then it completes the handshake. In case there is no response in 1 microsecond window, we get a PM NAC, and the side requesting should come out of L1 and get into active state. For exiting the PM state, one side sends an active, and that is transmitted to other side, and then the adapter sends active request and to the protocol there after retrain, and then when it gets the status to be active, it sends back the response, The other side also goes to retrain and sends the active request, and when it gets the response, it sends a response, and both sides come out of PM. Skipping this table, which just shows that in various states what requests could be serviced, and then at the end there are a couple of other examples. This is the example when we go into link reset, we are inactive, and software write sets the SBR to 1. So protocol layer sends the link reset request, which is forwarded to the other side, and it downs the link and sends the response back. And after that, this was for adapter. Then we do the same thing for RDI as well, so that phi is also in the reset. So, and for coming out, software writes SBR to 1, then we send an active request, and for the other side sends a status as reset, and then again we get the knob active request and we start the link running. Uh, and similar to reset, this is the example of link error. So protocol layers detects some error, then it will send a link error signal, and it will be propagated to the phi, and it will propagate to the other side, and the other side will go to the link error state and will send a response, and both sides will basically become in the link error state. And after a while, if the error is resolved, then we can set it to 0, and then both sides will come into the active state. So that's it. There were a bunch of topics or rules covered in this chapter that I skipped, but